the following lectures we will be discussing the eigenvalue spectrum of the angular momentum operator using operator algebra. In the last lecture, we had discussed that if there are two observables denoted by the operators alpha and beta, and if they commute, then they will have simultaneous eigengates. In fact, we considered first that the operator alpha has a non-degenerate eigenvalue, and let that eigenvalue be denoted by alpha prime. Then if the two operators alpha beta commute with each other, then we wrote down that alpha beta ket alpha prime is equal to beta alpha ket alpha prime, but ket alpha prime is an eigenket of the operator alpha. So, this is just a number multiplied by a number. Alpha prime is the eigenvalue and therefore, it is a number, and so this becomes alpha prime beta alpha prime. So, then we said that the ket which is represented by ket beta alpha, that ket p, if this is a non-degenerate eigenvalue, then ket p given by beta alpha prime must be a multiple of ket alpha prime, because this is an eigenket of the operator alpha belonging to the same eigenvalue alpha prime. This equation tells us that ket beta ket alpha prime is an eigenket of the operator alpha belonging to the same eigenvalue, and if it is a non-degenerate eigenvalue, then it must be a multiple of alpha prime. And so, therefore, this equation tells us that ket alpha prime is also an eigenket. Beta ket alpha prime is equal to beta prime ket alpha prime, and therefore, you will have ket alpha prime is a simultaneous eigenket of the operators alpha and beta. For alpha, it belongs to the eigenvalue alpha prime, and for beta, it belongs to the eigenvalue beta prime. We continue our discussion and we say that let us suppose this is a degenerate eigenvalue. That is, let us consider this simple case where the degeneracy is twofold. So, for twofold degeneracy, we can have two linearly independent kets. Let that be denoted as alpha alpha 1 alpha prime alpha 1 and alpha alpha 2 alpha prime alpha 2. That is, ket alpha 1 and ket alpha 2 are two eigenkets of the operator alpha belonging to the same eigenvalue alpha prime, and of course, they are orthonormal to each other. That is, we can always choose that alpha 1 is equal to alpha 2 this is 1, and alpha 1 alpha 2 this is equal to 0. They are a set of orthonormal eigenkets. So, this corresponds to what we have a twofold degeneracy. Similarly, we can have a threefold degeneracy also. Now, beta alpha prime is an eigenket of the operator alpha. So, therefore, beta alpha 1 and beta alpha 2 will also be eigenkets of the operator alpha, and therefore, they must be linear combinations of alpha 1 and alpha 2, that is beta alpha 1 is equal to C11 ket alpha 1 plus C12 ket alpha 2, and beta alpha 2 is equal to C21 ket alpha 1 plus C22 ket alpha 2. I hope I have made myself clear. I will repeat once again. It is a slightly tricky thing that beta alpha 1 and beta alpha 2 are also eigenkets of the operator alpha. So, they must be expressible as linear combinations of alpha 1 and alpha 2. Now, let the eigenket, let the ket which is an eigenket of the operator beta be denoted by beta operating on D1 ket alpha 1 plus D2 ket alpha 2, where D1 and D2 are numbers. Let this be a multiple of this D1 ket alpha 1 plus D2 ket alpha 2. Since alpha 1, ket alpha 1 and ket alpha 2 are eigenkets of alpha belonging to the degenerate eigenvalue, any linear combination is also an eigenket of the operator alpha. We now look for that linear combination which are also eigenkets of the operator beta. So, let that linear combination D1 ket alpha 1 and D2 ket alpha 2 be that linear combination which is also an eigenket of the operator beta belonging to the eigenvalue beta prime. So, here D1, D2 are just numbers. So, we are assuming that ket P, which is denoted by D1 ket alpha 1 plus D2 ket alpha 2, is a simultaneous eigenket of alpha and beta. So, let me work this out, then I will try to give you an example. So, D1 beta ket alpha 1. So, beta ket alpha 1 is C11 ket alpha 1 plus C12 ket alpha 2 plus beta plus D2 beta ket alpha 2. So, that is equal to C21 ket alpha 1 plus C22 ket alpha 2. Now, we must remember all these, here this is an operator, alpha and beta are operators, but here they are all numbers. So, this is equal to beta prime D1 alpha 1 D1 ket alpha 1 plus D2 ket alpha 2. Now, ket alpha 1 and ket alpha 2 are orthonormal kets, and so therefore, I can multiply by bra alpha 1, then this term will go to 0, this term will go to 0 and this term will go to 0, and we will obtain, please see this, that if the coefficient of ket alpha 1, this will be D1 C11, and from this side will be minus beta prime plus, there is ket alpha 1 is here, plus D2 C21, this is equal to 0. And then we will have D2 D1 C12, sorry, let me not use this paper. So, now if I equate the coefficient of get alpha 2, then we will have D1 C12 plus D2 C22 minus beta prime. This is equal to 0. This is a set of linear homogeneous equations. So, for non-trivial solutions, the determinant must be 0. So, we will have C11 minus beta prime, C21, C12, C21. Sorry, I am sorry. This will be yeah, that is all right. So, this was all right. C11 minus beta prime, C21, C12 and then C22 minus beta prime. This is equal to 0. So, this will give me two values of beta prime, and for each value of beta prime we will have two ratios. So, that we can always construct a set of orthonormal eigengates which are simultaneous eigengates of the operators alpha and beta. And let me take the same example as we had taken in our last class. Let me take the example like sigma x is equal to 0 1 1 0 and sigma is equal to 1 0 0 1. Now, here sigma x and sigma commute with each other. They are both Hermitian matrices. So, therefore, we must have a complete set of eigengates, but not all eigengates of sigma will be eigengates of sigma x. You can see that the eigengates of sigma x, as we had discussed yesterday in my last lecture, are 1 1 and 1 minus 1. You can put a root 2, so that they are normalized. On the other hand, here these are simultaneous eigengates, but these are also eigengates 1 0 and 0 1. So, these are eigengates of sigma, but not eigengates of sigma x. But I can always choose a linear combination, so that which are simultaneous eigengates of sigma and sigma x, and that linear combination in this particular case is this. These are the two orthonormal vectors which are simultaneous eigengate vectors of sigma x and sigma. Similarly, we had said that if we take this matrix, these are the Pauli spin matrices, this 1 0 0 minus 1 and then sigma again the same matrix 1 0 0 1, then sigma z and sigma commute with each other, but the simultaneous eigengates are 1 0 and 0 1. So, 1 0 and 0 1 are simultaneous eigengates of sigma z and sigma. This and this are simultaneous eigengates of sigma and sigma x and sigma. So, we have shown that if two observables, if two linear operators commute, then we can always construct a complete set of simultaneous eigengates. Now, we will discuss the operator algebra associated with the components of the angular momentum operator. Now, we will first, as we had mentioned in my last lecture, we will use this classical definition of the angular momentum operator. We will start with the classical L is equal to R cross P. So, that Lx is equal to y p z minus z p y, and similarly Ly is equal to x p z minus no, I am sorry, it should be y. So, this will be Ly will be z p x minus x p z, they have to be in the cyclic order, and Lz will be x p y minus y p x. However, we must be very careful that x and p x do not commute. X p x minus p x x is equal to I h cross. On the other hand, x and y commute, x y minus y x is 0, or x p y also commute, minus p y x is equal to 0. With this, we will now calculate the commutation relation between Lx and Ly. So, let me calculate the commutation between the commutator Lx Ly. So, this is equal to, we have to do this little carefully, putting things in proper order. So, Lx Ly minus Ly Lx, and Lx is equal to y p z minus z p y minus multiplied by Ly. Ly is z p x minus x p z, and the same thing in the reverse order, that is minus z p x minus x p z, and then y p z minus z p y. So, let me write out the terms fully. There will be 4 terms here and 4 terms here, and we must write them in proper order. And let me first write the first term, y p z z p x minus y p z x p z minus z p y z p x plus z p y x p z. And this will be minus z p x y p z, and then this times this will be plus z p x z p y, and then this that is plus x p z y p z, and the last term will be minus x p z z p y. So, you will see that, for example, this term, all of them commute with each other. All of the terms commute with each other. So, x, I can put them in any order. I can take the x here. So, x y p z p z, x y p z p z. So, this term will cancel out with this term. Similarly, here I can take z here, z square p x p y. This is z square p x p y. So, this term will cancel out with this term. But here we have to be careful. Please see that here you have PZZ and ZPZ. So, we have to be very careful. So, we can take these two terms outside . So, we will have y p x p z z y p x minus z p z. So, this is this term and this term. Similarly, here if I take out x p y, so then this will be z p z minus p z z. So, this we as we all know, this is equal to I h cross, and this is the opposite minus sign of that. So, this is minus I h cross. So, we will have, if I take I h cross outside, so we will have I h cross x p y minus y p x. So, this is nothing but L z. So, we will get I h cross L z. So, the left hand side as we had written before was L x comma L y. So, that L x and L y, the x component of the angular momentum and the y component of the angular momentum do not commute, and the commutation relation is L x L y is equal to I h cross L z. Similarly, you can write in the in cyclic order that L y L z y z x. So, I h cross L x, and then this will be z x is equal to I h cross L y. These are the important commutation relations, and which we will take as the starting point of our analysis. We will not worry about how we have got this commutation relation. We will start with this and build up the operator algebra to find out the eigenvalues and eigenfunctions of the L square and the L z operator. So, L x, so easy way to remember is this is x, y, z, and then y, z, x, they are all in cyclic order, z, x, y, x, y, z, y, z, x, z, x, y. So, these are the three very important commutation relations. As I had told you earlier, if I have an operator alpha, the square of the operator is defined as alpha times alpha. So, the operator L square is defined as L x square plus L y square plus L z square. So, what do I mean by L x square? That means L x plus L y plus L z. I will show that L square commutes with L x and because there is nothing sacred about x. So, L square also commutes with L y and L square also commutes with L z. So, although L x, L y and L z do not commute with each other, but each one of them commutes with L square. So, it was something similar to that we considered the matrices that 1 0 1 1 0 0 minus I 0. These are actually the Pauli split matrices 1 0 0 minus. These three matrices do not commute with each other. So, these are denoted by, you must remember them, sigma x, sigma y and sigma z. However, they each one of them commute with the sigma matrix, which is 1 0 0 1. Sigma x commutes with sigma, sigma y commutes with sigma, sigma z commutes with sigma. So, let me try to show that L square commutes with L x. I will show that this is equal to 0. Now, L square is equal to, so let me consider the left hand side. So, left hand side is equal to L square is equal to L x square L x plus L y square plus L z square. So, L z y square L x plus L z square L x. Now, this is obviously 0, because the first term is L x square L x minus L x square. So, if you write it out in detail, so this is L x minus L x. So, this is 0. Let me calculate the second term. This is the second term, and similarly I will give you one can calculate the third term, and one can show that the addition of these two terms are independently not 0, but the addition of these two terms will be 0. So, let me calculate the second term, which is equal to L y square. So, that is L y comma L x. So, this is equal to L y L x minus L x L y, sorry, this is y, L x L y L y. So, what we do is that I add and subtract, that is L y, I write this down as L y L x minus L x L y So, I have added a term minus L y L x L y. So, I add this term L y L x L y minus this term, I hope you have understood, L x L y L y. I have added this term and subtracted this term. So, this will be from the previous analysis we had shown that L x, in fact, we had shown little earlier that L x comma L y is equal to I h cross L z. So, this is L x L y minus L y L x. So, this is the negative sign of that. So, therefore, this will be minus I h cross L y L z. We must write them in proper order, that is very necessary. And then I take L y on the right side. So, I get L y L x minus L x L y multiplied by L y. So, this is also equal to minus I h cross L z. So, I get minus IH cross Ly Lz plus Lz Ly. I leave it as an exercise for you to calculate the third term, which is Lz square Lx, and carry out the same analysis, and the third term will come out to be the opposite of this, that is plus IH cross Ly Lz plus Lz Ly. And the total will be 0. So, that we have established that that L square commutes with Lx. Similarly, so we have 3 commutation relations that we have derived, and so the starting point of the theory of angular momentum, start with the commutation relation. We had earlier used differential operator algebra to write down the operator representation of the angular momentum operators. We had written that Lz operator was equal to minus H cross delta by delta phi. We do not worry anything. We just use the commutation relation, and in that sense it is slightly different from what we did earlier, and indeed we will get slightly different results. And so, therefore, the convention is that since we are depending only on the commutation relations, we use the symbol J representing the angular momentum operator. So, we replace L, Lx, Ly and Lz by Jx, Jy and Jz, and we start with the theory of angular momentum by saying that Jx, Jy, and we use the system of units in which H cross is 1, So, we say Jx comma is equal to I H cross Jz, but we assume H cross equal to 1. So, I Jz. Similarly, Jy comma Jz is equal to I Jx, and Jz, Jx is equal to I Jy. Further, we define J square, Jx, Jy, Jz. Further, we define the operator J square as Jx square plus Jy square plus Jz square, that is Jx, Jx plus Jy, Jy plus Jz, Jz, that is Jx square plus Jy square plus Jz square. And we assume, and as we have shown, that J square commutes with Jx, commutes with Jy and commutes with Jz. Further, since Jx represents the x component of the angular momentum, it is an observable. So, therefore, it must be represented by a Hermitian operator, by a real operator. Therefore, because Jx, Jy and Jz, Jx, Jy and Jz, because these are observables, Jx bar is equal to Jx, that is, they are all real operators. Jy bar is equal to Jy and Jz bar is equal to Jz, and of course, J square bar is j square. So, jx, jy and jz and j square are real operators. So, we assume just what is written on this paper and nothing else. Three things. We therefore assume first that jx and jy do not commute, and these are the commutation relations. We have got it in a certain way, but now this is our assumption. This is what we did even in the harmonic oscillator problem. We wrote down the Hamiltonian and then we assumed only the commutation relation between x and p. Similarly, here we assume the commutation relations between jx, jy, jz and jz, jx, and that j square j square commutes with this. And the third assumption is that since they are all observables, they are all represented by real linear operators. And therefore, since j square commutes with jx, I can have a complete set of simultaneous eigengates of j square and jx, or of j square and jy, or of j square and jz. Let me assume that ket lambda m represent simultaneous eigengates of j square and jz belonging to the eigenvalues lambda and m respectively. So, what I am trying to say is that j square, actually it is lambda comma m. It is not lambda times m, these are two numbers. So, ket lambda m is a simultaneous eigengate of the operator j square and of the operator jz. Let the eigenvalues and the corresponding eigenvalues are denoted by lambda m and jz operating on lambda m is equal to m lambda m. Lambda and m are numbers. Actually, we must remember that we have assumed h cross is equal to 1. So, actually what we are saying is this is lambda on the right hand side is actually lambda h cross square lambda m, the h cross square is hidden, and this is m h cross lambda comma m. So, I want to solve this eigenvalue equation. That is, we want to obtain simultaneous eigengates, a complete set of simultaneous eigengates corresponding to the operators j square and jz, First, I consider this operator j square minus jz square. Jz square is jz operating on lambda m, and this is lambda m. So, these are orthonormal gates because they belong to real Hermitian operators, they are eigengates of the Hermitian operator. So, please see j square operating on ket lambda m, this is equal to, the left hand side remains the same, lambda, and jz operating on lambda m is m. If I operate again by jz, it is m operating m jz this thing, so m square. So, this becomes m lambda minus m square ket lambda m. This is just a number because these are numbers, these are just eigenvalues, this is the operator. So, this becomes, and if these are orthonormal kets, then this becomes lambda minus m square. Okay. Now, let just for the sake of convenience, I represent this by ket p. So, j square, as we remember, is equal to j x square plus j y square plus j z square. So, j square minus j z square is just j x square plus j y square. So, this left hand side, so the left hand side, this quantity left hand side is equal to bra p j x square j x plus j y. So, I write this as ket p, I hope this is clear, plus ket p bra p j y. Let this be ket q, j x ket q, ket q is defined as, so ket q is defined as j x ket p. So, the conjugate imaginary of that is bra q, this is bra p j x bar, but j x bar is j x because it is an observable. So, bra p j x is just bra q. So, this is bra q plus j y ket q, let us suppose this is ket r, then this is bra r. So, my left hand side is bra q ket q plus bra r ket r. So, the left hand side is greater than or equal to 0 if ket q is a null ket and if ket r is a null ket. These are two positive definite quantities or can be 0 also. So, unless each one of them is 0, the sum is always positive. So, we get the remarkable result that lambda must be greater than equal to m square. So, we find that from just by operator algebra that this eigenvalue of j square lambda must be greater than or equal to m square. Okay. Now, as we had done, so we have the very important result that first of all we write down that let ket p, which is ket lambda m, is a simultaneous eigenket of the operator j square and j z. So, we will pet p is equal to ket lambda m. Then we have derived the very important relation that lambda must be greater than m square. Okay. Now, we define in the harmonic oscillator problem, we had defined two operators a and a bar, which we had denoted by, represented by what are known as annihilation and creation operator. Here we define two operators which will be called ladder operators. The two operators j plus, which is equal to, defined to be equal to, when I have 3 equal to signs, that means defined to be equal to j x plus I j y, and the adjoint of this is j x bar, which is j x minus I j y. So, we define another operator j minus, which is the adjoint of this operator, which is j x minus I j y. So, for example, j plus j minus is equal to, you have to be careful, j x plus I j y into j x minus I j y. Now, on the first side you will say this is a plus I b and this is a minus I b. So, if I multiply these two out, I will get a square plus b square, but that is not correct. We have to be very careful in multiplying in proper order. So, this will be j x which is j x square, then j I times I is minus 1 minus plus j y square, and then minus I if I take outside, it will be j x j y minus j y j z, because the operators do not commute. So, this is the commutator of j x comma j y. So, this we had shown that this is equal to, this part was equal to I h cross actually. So, I j z. So, I times I is minus 1. So, this becomes plus j z. So, this becomes j plus j minus becomes j x square plus j y square plus j z. I leave it as an exercise for you to show that you take it in the reverse order, that is j minus j plus will be equal to j x square plus j y square, but here it will be a minus sign. Yeah. I leave it as a very simple exercise for that. Okay. Now, let me consider the commutation relation. We know that j square commutes with j x and j square also commutes with j y. Okay. So, j square will commute with j plus. J plus is, if you remember that we had defined the operator j plus as j x plus I y and j minus as j x minus I j y. So, j square will commute with j plus and j minus. So, please see this, j square j plus is equal to 0 or j square j minus is equal to 0. So, therefore, j square j plus, leave some space here, is equal to j plus j square. I multiply, I operate this on the Eigengate lambda m. I operate this on lambda m. Then you see j square operating on this thing is, this is the Eigengate. J square operating on ket lambda m is equal to lambda operating on this thing. So, this is an Eigengate. So, this becomes lambda, and lambda I can take anywhere. So, lambda j plus ket lambda m. Thus, if what we had started out with j square ket lambda m is equal to lambda ket lambda m. Thus, if ket lambda m is an Eigengate of the operator j square belonging to the eigenvalue lambda, then j plus ket lambda m, because j plus ket lambda m is also an eigenket of the operator j square belonging to the same eigenvalue lambda. So, we must expect degeneracies, degeneracies. Similarly, let this be, I denote by ket r, let us suppose. So, I have j square ket r is equal to lambda ket r. Now, I again do like this. So, j square j plus is equal to j plus j square. I operate this on ket r. Now, j square ket r is lambda, so lambda j plus ket r. So, I put this inside the bracket, I put this inside the bracket. So, then j plus ket r is also an eigenket, provided it does not become a null ket. If it becomes a null ket, then of course, it is a trivial solution, because null ket is always an eigenket and anything can be an eigenvalue. As I had mentioned earlier, if I have any operator alpha operating on null ket is always 0. So, this is a trivial solution. So, if you have, so therefore, we conclude that if ket lambda m is an eigenket of j square belonging to the eigenvalue lambda, then j plus ket lambda m is also an eigenket of the operator j square belonging to the same eigenvalue lambda, and similarly, provided this is not a null ket. Similarly, j square operating on j plus ket lambda m will be again lambda j plus ket lambda. So, we must expect degeneracies. So, if ket lambda m is an eigenket, then j plus ket lambda m is also an eigenket belonging to the same eigenvalue lambda, provided it is not a null ket. Then j plus ket lambda m is also an eigenket belonging to the same eigenvalue lambda, provided this is not a null ket. And then j plus ket lambda m is also an eigenket belonging to the same eigenvalue lambda. In the next lecture, we will show that j plus ket lambda m is also an eigenket of the operator jz, but now belonging to the eigenvalue m plus 1, j plus 1 ket lambda m. So, therefore, we will show that j plus ket lambda m is a simultaneous eigenket of the operator j square and jz. For the operator j square, it belongs to the same eigenvalue lambda, but for the operator jz, it belongs to the eigenvalue m plus 1. Thank you.